Greetings and welcome, friends. Mr. Waddy here. We are in section 5.4. We are talking about equilateral and isosceles triangles. Triangles, if you will. We are talking specifically this moment about the base angles theorem, B-A-T. Bat. Here we go. It says a triangle is isosceles when it has at least, Malik, two congruent sides. When an isosceles triangle has exactly two congruent sides, these two sides are called the legs. Ah, I get it. The angle formed by the legs is the vertex angle. Wow, I would not have remembered that from teaching geometry 10 years ago. Vertex angle. Wow. Wow. Guys, they got me. They done got me, Aiden. I don't know. I'm learning something here new today. That's okay. The third side is the base. Yeah, I like that. And the two angles adjacent to the base are called base angles. I also refer to base angles as being opposite of the legs. All right, opposite of the legs, those base angles. All right. Does that make sense? When I say opposite of the legs, you guys know what I'm talking about? That means they are the non-included angles of those legs. I don't even know how to sign my name, I'm sorry. Those be the base angles. And it turns out there's some properties we can learn about the base angles with respect to the legs when we have an isosceles triangle. It's called the base angles theorem. It says this: if, notice this, wait, a theorem and the converse of the theorem. Actually, I usually refer to this as the base angles converse, but that's okay. If two sides of a triangle are congruent, I believe it, then the angles opposite of them are congruent. Opposite, congruent, opposite, congruent, okay? That looks like that'd be like some sort of like, I don't know, angry emoji with like red cheeks or something. I don't know, I think so. Yeah, I could see like a Pikachu face forming in there somehow. Yeah, so there you go. Base angles theorem makes sense. The converse of the base angles theorem, I should just be able to, for a converse, just swap the hypothesis and conclusion. I think you guys agree. If the two angles are congruent, two angles in any triangle, then the sides opposite of them are congruent, right? Yeah. Not bad, not bad. Let's see. So I showed this to my students using some geometer sketchpad. Notice I've got a triangle that has two congruent legs because they're both radii of the same circle. And no matter where I draw this, for all possible isosceles triangles, notice that these angles, those base angles, happen to be congruent. All right? Good times, good times. But let's prove it, because that's like a visual proof. Yeah? Let's prove it, though, because I don't know if you should just believe me because I told you something, or because you read something in a math book somewhere. Actually, there have been mathematical claims that have been thought to be true for like generations that are then proven false much, much later. So we don't want to just believe something because we think it's true or because a lot of smart people think that it's true. So here we go. Given AB is congruent to the AC, AB congruent to the AC. Here, let's see. There's a better line. I'll give my given, all right? AB is congruent to the AC. Prove that these angles are congruent. So that's what I'm hoping for. That's what I'm aiming for. But let's see if that's the case. Does anyone have some suggestions? Let's see. What is this orange line that they drew? They said that these two angles are congruent. This is it's a type of bisector. Let's see, draw AD bisecting angle BAC. And so we can do that. That's just like construction of an angle bisector. All right. Right, there is exactly one way that I could cut that angle in half, right, that makes its two halves congruent. You guys agree? All right, what's another fact that I could claim? What's something else? Because that one probably would not have been obvious, but that's a good trick, right? What's something else that I can say is true regarding maybe these two little triangles?
That the angle of the two little triangles.
We don't yet have enough information to prove that this is a right angle yet.
But you just said bisector.
But it's an angle bisector. It wasn't a segment bisector. That wasn't the way that I drew it. Theoretically, I could have drawn it that way.
But like those ones, never mind.
Yeah, that will eventually be true. That definitely will eventually be true. So let's see. AD is congruent to itself. Why is that true? Oh, wow. Yeah, I was jumping the gun. Reflexive. And now, what about these little triangles? I could say that these little triangles are congruent, right? Let's see. Let's call it triangle ABD. Is congruent to whom? ABD what's the corresponding? ACD, yep. And the reason that's true is side angle side. And now watch this trick. Are you ready for this?
No.
Angle B is congruent to angle C. The reason is because the corresponding parts of congruent figures, in this case, triangles, are congruent. Say, pay, say, tay, say. But if I say it like that, will you remember it more likely? How about again? Say, pay, say, tay, say. Yeah. Corresponding parts of congruent triangles are congruent. So for instance, another claim I could make using the same reason, I could also say this guy is congruent to that guy. Because I already know those triangles are congruent, and therefore their corresponding parts are congruent.
What is that for?
Corresponding parts of congruent triangles are congruent. All right, so we done just proved ourselves a base angles theorem. And some of you guys I know had already started the tonight's homework quest, which is cool. I'm fine with that. And you probably noticed like some of these problems aren't that bad. All right, so here it says, watch this. In this triangle, DE is congruent to DF. Name two congruent angles. Which angles are they, friends? Yeah, just wait for Alyssa to get back. All right. Okay, so does that make sense? That makes sense? That just makes good sense, friends. Ooh, how about these ones? I think I gave you guys a copy of this one. Yeah? How about this? If HG is congruent to HK, what are two angles that are congruent? Angle G and HKG. I knew which one you were talking about. But we got to make sure they know what one they're talking about. Let's see. Another theory. They said if angle KHJ, okay, let me draw this in a different color. This angle is congruent to KJH, this angle, then what do I know?
And JK is congruent to KH.
JK is congruent to KH. Right? If there are two angles in a triangle congruent, then the sides opposite of those angles are congruent. And then I could actually even do by transitive property say that this guy is congruent to that guy. But that's just crazy, friends. All right. Are you guys ready for some corollaries?
What are corollaries?
Find out.
Does anyone remember what a corollary was? A corollary was a theorem that was just like the smallest step from like a bigger theorem that did all of the work. A corollary would be like, it would have been a postulate if it wasn't for the fact that a theorem came before it. All right, like it's almost obvious.
So if we were going to write this, we would have to write C back. So,
I'd probably understand that, but yeah, I mean, at some point we got to make sure that we got all these acronyms together. So this is saying this: if a triangle is equilateral, then it is equiangular. Let's put that to the test in Geometry Sketchpad. Let me measure this. Let me move this until the that is going to be 6.33. And man, I can't do it.
Let's say that.
why is that
Point.
Did it! Nailed it! Stuck the landing. Give me the gold medal. Wow! You guys saw that recorded for the internet? That's the only time it's ever going to happen. So, notice this. When all three sides are congruent, ding, 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 what types of angles do those happen to be? 60 degrees. And by third, what would the third angle be? Another 60 degrees, because trisum theorem, 60 plus 60 subtracted from 180, it's got to be another 60. It is the only way, the onlyest of ways. And yeah, that's the corollary to the base angles theorem. And then also the corollary to the converse of the base angles theorem is true. If you got all the angles, then yeah. Let's see, what happens if I make this a 60-degree angle? Can I do it? Close enough. Let's see, that's 16.39, that's 16.39. Let's measure it. And yeah, there's a visual that kind of makes sense. Kind of makes sense. Because I didn't have it exactly the same in my measurements. All right, so there's some corollaries. Let's put those to work. Put them to work for us. Here's example 2. All right. Find the measures of angles P, Q, and R. 60. Actually, the theorem, the corollary that we just did, notice it just says it's equiangular. So let's actually say this. That would mean that measure. All right. Let me get there. Angle P is congruent to angle Q is congruent to angle R. The reason that's true is the corollary. Corollary of which theorem? Well, these were the sides. Corollary of the base angles theorem, right? If their angles are congruent, then their measures are equal. If their measures, let's see, all of these angles add up to 180. Let's see, that was Def Kong right there. According to trisum theorem, I know that those all add up to what? 180. Then using substitution, let's see, actually I'll just do this. There we go. I just want to point out, like, this is, it's quite a bit of work, but we are going to prove that equiangular triangles measures are 60 degrees one way or another. That was a substitution. Now, Lauren, I think you agree we could combine like terms here, which is actually a type of undistribution or whatever, but So that's 3 times the measure of angle P equals 180. I'll just call that simplify. Sometimes people might call that a type of distribution, but it's reverse distribution. What could I do next? What's the measure of angle P, which you guys have known since the beginning of this problem? 60 degrees by division property. Div it. Div props. Div props. Okay, so, and then if that one's 60 degrees, then all 3 of them are 60 degrees by transitive property of quality. Whoa! Wow! That ended up being more than I thought. Okay. Oh, here we go. This one's more interesting. Interessante here. All right. Here we go. All right. Find the values of x and y. Guys, I love it. I love it. Are you ready for this? I'm ready. All right. Are you ready? I'm ready. I'm ready. Let's see. Here I know this is an equiangular triangle. By the corollary of the converse of the base angles theorem, I know that these 3 sides are congruent. True story, right? That's true by the corollary of the converse of the base angles theorem. Right? Where did? All right. A converse is when the if-then statement had its hypothesis and conclusion swapped. Yeah, go back and check it. You'll see that the converse is just the reverse ordered. All right, so that's true because of that. I also know this is true. Why is that true? That's true because of the converse of the base angles theorem. That's just plain converse of the base angles. Okay. So, what statements about x and y can we make now that I know these congruences? Well, y equals 4.
Oh, yeah.
Okay. That's just true because of def of Kong once I knew those sides were congruent. I also know that x plus 1 is equal to that measure, is equal to that measure, is equal to 4. All right? By like a transitiveness, subtract 1 from both sides, and we will end up with x equals 3. All right? I kind of like these ones where they've got like nested triangles put together. Oh. Wow, guys. What is this length?
Well, that's 8. 8.
It's 8.
No.
This length is 4. Does anyone, this is like, we won't see this until like chapter 9. Does anyone know the length of NM?
With 8. 6.
This is 60 degrees.
9.
It turns out this is 30 degrees and this is 90 degrees. And I know that merely because this length, this is twice the size of this length.
Oh, so it's the Pythagorean.
And this will actually be, if this is 8 and this is 4, this will actually be 4 square roots of 3. But don't you worry. That's just like spoilers for some of chapter 9. Spoilers. All right, here we go. And you guys definitely need to know this if you're ever going to save a life as a lifeguard. Just so you're aware, like you can't even, they won't even give you like the little floaties with the circle tube thing, the life preserver, until you know this. It's true. What do we know about this? In the lifeguard tower, PS is congruent to QR. All right? And QPS is congruent to PQR. QPS, oh dear. So that's the entire angle is congruent to that entire angle, right? Did I read those right? PQR. PQR, true. Okay. And PS is congruent to QR, what do they want us to do? Did I miss the part where it asked us to do something?
It's only a multi-set problem.
I'm assuming they want to. Let's see, where does this problem end? Yeah, did I cut something out of this problem? Well, let's just tell me things that you can know. Yeah. Let's see, angle. Oh, PQ is congruent to itself.
Yeah.
Why is that true? Because of reflexive. Okay.
Looking at those two triangles are congruent.
Now that we have that, let's say that triangle. Maybe I'll label it in the same order here. QPS is congruent to which triangle? Let's see. QPS. So it's got to be PQR.
Yeah.
Why is that true? SAS, side angle side, because we happen to have two sides and an included angle that are congruent. Wow. Okay, so SAS. Then I could say because of SAS, I know that angle 3 is congruent to angle 4 because corresponding parts of congruent triangles are congruent. Not with the problem that I've given us.
Because it's the same cool people clearly, totally.
Yeah, I think it does. But yeah, so next time I teach this problem, I'll have to figure out where the rest of the problem went. But anyways, thanks for watching, internet friends.